Okay, good afternoon. Today we'll talk about remote sensing as climate change impact on hydrological regime. So the outline of my lecture is basically first I will talk something about climate change, then land use land cover change and climate change because it goes together, then space technology application, framework and establishment of process-based hydrological model for climate change studies, and I will show you some results. So climate system and climate change. The climate system is a very complex as there are multiple interactions between atmosphere, land. To understand the climate change, it is necessary to have a continuous monitoring, synoptic coverage, 3D measurements, and long-term monitoring. Climate change, why? So there are two regions of it. One is the natural region. There is a natural region of climate change and there is a human induced. So first let us discuss about natural region. There is a concept of non-COVID region. It says that Earth change its eccentricity. It means that that Earth is little eccentric, so it may change, and total cycle is around 100,000 years, and flux change is 0.014% to minus 0.017%. Change in obliquity. What is obliquity? Tilt in Earth axis varies from, currently the axis of the Earth is 23.5, but actually it varies from 22 degree to 24.5 degree. So when axis changes, there is a change in seasonality in the climate. But the cycle is 41,000 years. So if you see earlier it was 100,000 years, now it is 41,000 years. Third one is the orbital precision. It is nothing, simply ball of the Earth tilt, cycle is again 22,000 years. So these are the three changes occurs, but changes are so slow, it occurs in thousands of years, less year. So there is no need to worry about it. Because human life is only 100 years. If you talk about 7 generation or 10 generation, maybe 200, 300 years. So we don't have to worry about it. Second is climate change where? If you see here, this graph, this is from 1880 to present, and you find if you consider land and ocean together, there is a change in the temperature. If you see ocean only, the change is less, while if you talk about land only, you will find lot of change occurs. It means it is on the land where this temperature change occurs, and on the land. So we can conclude that because of the human intervention, there is a change in global temperature. Now, human activity is causing climate change in GHG, greenhouse gases, and LULC change. Again, it is LULC change also GHG, I will discuss. So what are the greenhouse gases? You are aware about it: carbon dioxide, nitrous oxide, methane. They are the famous greenhouse gases. But let me tell you, another very important gas is the water vapor, which is also it also create the it increase the temperature. You can experience it. Suppose today there is a cloud in the night, then you will find it is not so cool. If cloud is not there, then you will find it is very cool. It means because of the water vapor, that energy is not going away from the earth. It is trapped between the cloud and earth, and then you will have a warmer. So how it works, how it is increasing greenhouse effect, energy is released by the earth. If there is a greenhouse gases, it will not completely go away. Something will go back, come back to the earth, and it will be absorbed by the surface. So it will increase the temperature. That's how greenhouse effect will be created, and you will have a global warming. Climate change. So land cover change, general term for the human modification of Earth's terrestrial surface. It means what we are doing, we are going for urbanization. We are cutting the forest, we are constructing the road, we are constructing the buildings. So basically this is a human modification of Earth terrestrial surface. So let us see how it is influencing and how it is releasing the carbon to the atmosphere. LULC change can increase the release of carbon dioxide to the atmosphere by disturbing the terrestrial soils and vegetation. For example, when you cut the forest and convert it into the agriculture, so what you are doing, you are basically removing the sink of the carbon. Forest is one of the biggest sink of the carbon. So you are reducing it. So once you are reducing the sink means good amount of carbon is available to the atmosphere, so you will have a global warming. Second one is, when you are cultivating the land for agriculture, so you are doing tillaging. The tillaging pulverize the soil and soil release the carbon to the atmosphere, so again it is increased. For agriculture, a lot of paddy cultivation occurs, so paddy cultivation release the methane, so you will have a burn. Now, for agriculture, you are giving input like nitrogen. So it will have a nitrous oxide. So again it is a gas for a greenhouse effect. When you are converting agriculture to urban, then you are creating the heat island. Land cover change also enter the reflection of sunlight from land surface. For example, any land cover change like forest to agriculture, basically albedo change. Albedo means reflectance. So when reflectance decreases, it means the light is coming to the ground and you are increasing the temperature. Classical example is that the snow melt. When you are removing the snow because of this global warming, snow area of the Arctic is decreasing. It means the snow has a very highest albedo. It is sometimes it is 90% or 95%. But there is no snow, then albedo will reduce, a lot of energy will be absorbed by the earth. So again it will increase the temperature of the earth. More also again will create the problem. You are changing the LULC, this is a very classical thing. Basically what you are doing, you are not only changing the evapotranspiration, basically you are altering the evapotranspiration. Not only altering the evapotranspiration, but also you are reducing the interception. If you look at the hydrological cycle, in a water balance mode, if you change one component, entire hydrological cycle you are entering. So this is creating direct impact on hydrological cycle. It is look at this. You see here, this is the black line, and black line shows that average snow cover of Arctic region, Arctic Sea, and you find it is very high, comparatively it is high. While in 2008 it is reduced. So it means snow area, highest area of Arctic region is reduced. So once it is reducing means what? Basically it is an alarming situation. It is showing there is a increase in the Earth's surface temperature. So space technology offer you continuous monitoring, synoptic coverage, it gives you 3D measurement, and it gives you long-term monitoring for atmosphere, land and ocean. Now, let us discuss different instruments available, different satellites available for measuring these parameters. So far you heard about our Indian satellite like ResourceSat, Cartosat, maybe some of you may be aware about some more satellites like OceanSat. In foreign satellite like Landsat, Iconos, Quickword. But these are the satellites which is used for some, land surface mapping. Maybe land use land cover, maybe ocean, maybe snow cover area. But for measuring the gases, there are different set of satellites. One such type of satellite is OCO2, Orbiting Carbon Observatory 2. It was launched by NASA. It was launched in July 2014. It measured the carbon. The sample area is 3 square kilometer. It has a 3 bands, 0.76 which is oxygen band, 1.61 and 2.06 micrometer is a carbon dioxide band. What it does actually, satellites, it has a 3 bands. So 1.61 actually most of the gases in the atmosphere, it doesn't absorb it is not sensitive to this band. However, carbon dioxide is very sensitive to this band. So anything in the carbon dioxide will change the reflectance of this band, absorbance of this band. So that's how we can estimate the carbon dioxide. But then it is important to calibrate. You should have some reference gas. So with oxygen band is 0.76. So you can compare, you can make the ratio and you can really find out how much carbon dioxide is increased. So you can get where it is increasing on entire globe, where it is increasing and where it is decreasing with 3 square kilometer grid size. So this is a very important satellite which gives you the carbon of the world, global carbon. It gives the global carbon cycle. So it will improve, not only this, it will improve further the global carbon cycle models, which will help us to tell the global warming in the future. This is dedicated for carbon dioxide. However, there is another satellite known as Iskiamaki. It is from Europe, and this satellite gases like O3, NO2, BRO, SO2, all this, methane, carbon monoxide, carbon dioxide. It's a very useful satellite. People have used it. People have mapped entire world. It works with the wavelength of 240 nanometer to 2380 nanometer. So such type of CO2 products are available. You can see this is a CO2 level, and you can see each pixel things are available. Then to measure the ice and elevation, ice set and cryosat, these are the two satellites. Currently it is a cryosat because now ice set is no more working, and it gives the ice sheet mass balance, cloud and aero height, land topography, vegetation characteristics. And it works on the laser altimeter system. It has a laser altimeter. It's just like radar. The signal goes back, the position of the satellite. It knows the distance traveled by the laser. So it will calculate the distance. So elevation of the satellite minus the distance is equal to the elevation of the snow. So any change in this elevation of the snow will tell you the depletion of the snow. That's how it measures the snow. You can see here, basically initially while you see the purple line, so snow cover was crossing that, but now it is not crossing. So we can say snow cover is reducing in this area, Arctic area. Then there are some more satellites like CloudSat and Calypso. CloudSat has a cloud profiling radar. So a radar that is more than 1000 times more sensitive than existing. Detect raindrop size particles, detect the much smaller particle of liquid water and ice that constitute in large cloud masses that makes our weather. Calypso stands for Cloud Aerosol Radar Pathfinder Satellite Observation. Launched in 2006, it measured not only cloud but aerosol. But then a train is basically atmosphere train, where just like a train you have a series of satellite, and within 2-3 minutes at a particular point all satellite passing. For example, it is like that. First satellite is the OCO, orbiting carbon observatory. After 15 minutes, at this point Aqua will come. After 15 minutes, 30 second CloudSat will come, then Calypso will come, Parasol will come, Aura will come. So all these satellites will come at this point. Within 2 minutes, all these satellites will pass. So at a time, almost at a time, you will map all this global warming related parameters using these satellite systems. So this system is known as the A-train, just like a train like bogie. Different satellites will come, it will pass. You can capture simultaneously. You can capture the aerosol, you can capture the moisture, you can capture the rain, you can capture the cloud, you can capture the carbon, all these parameters, you can capture the CO2, these parameters you will get almost simultaneously. So these are some satellites which now details is available in this table, like Aqua, what is the sensor. So Aqua has a AMSRE, CERS, MODIS, AIRS, AMSU, then CloudSat has a CPR, cloud penetrating radar. Calypso, these are the sensors. So this is a table, maybe you can use it for your further study, which will give you in detail. Now there is another satellite, ESMOS, soil moisture and ocean salinity. This satellite is launched in 2009. It is working. Now life is over, but still working. It mapped the soil moisture with an accuracy of 4%. 4% means suppose soil moisture is 20%. So the accuracy is 4% of that 20%. So it is very high. Similarly, it also measures the ocean salinity, which will give the idea of the global warming and how that absorption of the light and the things, and it improved the understanding of the water. Now, very soon NASA is going to launch this satellite, soil moisture active and passive. You are aware that soil moisture can be measured using the passive microwave as well as the active microwave. The advantage of passive microwave is it gives the everyday soil moisture. But disadvantage is the resolution is very poor. It gives you 25 kilometer by 25 kilometer. You must have heard about AMSRE. It gives the soil moisture for entire world. Every 3 days it is available. But the resolution is 25 kilometer by 20. Then you can go for active microwave. Resolution is very good, maybe 5 meter, 10 meter. But disadvantage is that it will come after 20 days, 20 or 30 days. So temporary resolution is very poor. So to combine both, we can optimize. We can get the advantage of repeativity of passive microwave. We get the advantage of spatial resolution of active. So NASA is launching soil moisture active passive sensor known as SMAP. It will give you a better soil moisture with better repeativity, with more spatial resolution. GIS satellite. This is the, you may be aware, GIS satellite is it basically tells about the terrestrial water storage of the world. So you can, the resolution is 300 kilometer by 300, or nowadays they are giving the product of even 100 kilometer by 100 kilometer. What you get here, you will get total water storage, and so then you subtract the soil moisture and everything, you will get the groundwater. So this is very useful for hydrological science. MODIS, you are aware, it will not only give you the land, it will also give you the atmospheric product like aerosol product, total precipitable water, cloud product, atmospheric profiles, graded atmospheric cloud mass. Land, you are aware about it, leaf area index, evapotranspiration, then surface reflectance, temperature and emissivity. Ocean also, it gives many other products like chlorophyll content and all these things. So MODIS is quite famous. You can download the data from the website. It will help us to apply in the. Let us see those satellites. Maybe slide is not visible. It may take some time. I can tell you there are different set of satellites. Like we have megatropics, which tells about the rainfall as well as the ocean condition, rainfall, especially in the ocean region. We have Saral Antarctica, which will give the idea of the elevation of the water and wave heights. We have ocean set also. So these are the satellites which will help us to see the water cycle. But then next question is, I'm sure I think you are not you are not getting any slides here on the screen. There is some problem. People are working on it. But meantime, I can have a discussion. So what I will do now after this, we have tried here that how this remote sensing information can be assimilated in hydrological model, and all the GCM data, if there is change in the temperature, if the change in the precipitation in the future, let us say 2025, 2050, 2099, if it takes place any changes, I will force my model of these changes and I will see how runoff in the river will change, how evapotranspiration will change, how waste flow will change. So this is the study we have carried out, and we have got some interesting results. So maybe I will discuss once these are ready. Probably our people are working on it. Sorry for this disturbance. Okay, so I told you we have a SARAL satellite. SARAL means satellite with Argos and Altica. Is a cooperative altimetry technology mission for ISRO and CNES, France. CNES, France. It is a France space agency. So Altica is the instrument which is Ka band with altimeter. LT means altimeter, Ka means Ka band with altimeter. So what it does, it just like radar, it sends a signal, goes back and then measure the height of the what we call ocean surface topography with 8 millimeter accuracy. Not only that, at IIRS we have worked on the different dams like Terry Dam, Macan Dam, and also at the seaside also, and we found the accuracy with the centimeters, which is very good. Suppose Terry Dam, what is the elevation of the water, what is the depth of the water? Immediately with this we get. Only thing is the repeativity is very poor. So maybe it is good for in future if repeativity will increase. Every 3 days or 4 days I can monitor my reservoir. INSAT 3D is dedicated for weather, is a meteorological data relay and satellite aided research and rescue satellite. It provides an operational environment and storm warning system to protect life and property, to monitor surface and carry out oceanic observation. Basically, the most important thing is it has a payload, logical payload. It gives you the temperature. The beauty of this satellite is it basically not give you the temperature of the surface. It is sounder. So you get temperature at, let us say, on the surface of the land, at 1 kilometer, at 2 kilometer, at 3 kilometer, at 4 kilometer. So you see all the profile, atmospheric profile of temperature. Not only temperature, some other parameter also will calculate. It will give you many more parameters like cloud top temperature and all this. So this will certainly is improving our all mathematical model for weather forecasting. This is very important and very useful satellite for weather forecasting. Nowadays, whatever information you are getting, even in TV also, you are getting from INSAT, or earlier it was Kalpana. If you want to see the product, you go to www.imd.gov.in. Okay, now let us talk something about GCM. What is GCM? GCM is General Circulation Models. It is basically based on the energy and change how the energy will change. It will calculate the temperature, it will give you the precipitation, it will give you the humidity, all these parameters it will give. But the resolution is very poor. Resolution is 2 degree by 3.75 degree. So this GCM is not fitting in hydrological process. Let us try to understand this. If you see this slide, if you see the GCM, it is a better simulated GCM, means spatial scale is 500 km by 500 km or 200 km by 200 km. Nowadays even they are giving 100 km by 100 km. So they are predicting well. Temporal scale, mean annual, and they are predicting well. But daily they are not giving nice what we call prediction. It is only seasonal and annual. They are giving good information of 500 hectopixel, means around 5 kilometer or maybe 4 kilometer. But on the ground, I want information on the ground. And working variables like wind, temperature, air pressure, they are predicting well. But for hydrology, I need information of the soil moisture, evapotranspiration, rainfall, which is not good. I want information on earth surface. I want daily data, and I want resolution of 0 to 50. So much nice thing resolution I want. So I am not getting from GCM, so I have to downscale. There are different downscaling technique. One technique is the dynamic downscaling. Second technique is the WRF is the example of dynamic downscaling. Second one is the statistical downscaling. There are different techniques are. So we downscale it and then we use this data for future prediction. So we incorporate this information like rainfall, temperature, we incorporate this information into our hydrological model. So now let us start how we see the change in the hydrological regime. So framework of the system. So first we have to select the model. We will for such type of changes. So should be a basin scale model because the climate models are macro scale, so we should use macro scale model so that we can work out for the river basin. If you are thinking that GCM or downscale model, what is the temperature change for a small area, maybe 3 km by 3 km, 5 km, no, it is wrong. You will not get it. You will get only for 50 km by 50. So macro scale model is required. Should also consider subgrid variability, should have physical basis, should estimate all component of hydrological regime. It should be open source, why to purchase, and should incorporate interbasin transfer. So we have used such, so this is one model which has all the capability whatever I have listed. This is known as variable infiltration capacity model. It considers subgrid variability. It also estimates base flow which is required for any change. Water balance is there, even energy balance is there. So for future climate change, any change in energy exchange, it will give the information how snow will change and how that rainfall will change. So this is open source. Now various modes. So for water balance, it compute all water balance component. Other modes are also available. So I am talking about water balance currently. SWOT model or other model, you have to define your watershed boundary. Similarly here also, you have to have a boundary map. So again, procedure is same. You should have a DEM, then you can delineate the flow direction map, flow accumulation map, drainage network, then delineate the watershed boundary. Second is generate the land surface input data like vegetation library parameter. What are these library and parameter? I'll come to. Then soil parameter. So prepare the soil parameter file. Then generate the meteorological forcing data. You can use any forcing meteorological information by either you can take GCM data, still GCM data, or you have your own data, you can use it. Then download and compile the big source code. It run on Linux. Modify the global control file and run the model. These are the 6 steps. So these are the parameters. Vegetation parameter file. So it consists what is the fraction of the vegetation it is there, what is the fraction of water it is there in a pixel. So it considers subgrid variability. What it does, it estimates water balance, what is the fraction of bare soil. It calculates water balance. Then it route the water. So it calculates the final water balance of a pixel. Then route to the outlet. So this information you have to provide. CV means fraction. You need not to worry about this font because there are listing of various parameters. But if you are interested, you can go to the website. You write in Google capacity model, and you will get all this information. Then there are different other vegetation library. It will ask you. As I told you, once you know the land cover, then model will not interested in land cover. It will ask you what leaf area index. So leaf area index you define here. It will ask you what is the albedo. Albedo you define it. It will ask you what is roughness. Roughness. What is the height of the tree. All these parameters you have to give information here. Then soil parameter file. Different parameters of soil like hydraulic conductivity, bulk density, type of the soil. Then organic matter content, many parameters like them. So all these parameters will ask you have to find those parameters. Next step is, there is again a problem, but I am sure you must be hearing my voice, so I can continue because already yesterday also I have discussed a lot about modeling. So what I will do, a forcing parameter, I will change those forcing parameter. What I will do, like for example, in temperature today, it is let us say 20 degree. Because of the global warming in 2050 it is 22 degree. So I will change that parameter. Suppose precipitation, okay, so what I will do now, using that model, we will see the impact of climate change on hydrology. So step by step I will discuss. First one is, as I told you, first step is the boundary. So what we do, we take the digital elevation model. This is the DEM. Then flow, you have to fill the same flow direction, flow accumulation, define the stream segmentation, watershed delineation, and aggregation if you want. So these are the steps. Yesterday already I have discussed all these steps. So once you do this, so your now watershed is decided and delineated and it is fixed. Now next step is LULC map, land use land cover map. So different classes you can see. This is for 2008 land use land cover map using the satellite data. Then next step is create a grid map of your area. So because we have to calculate the water balance, so this is 5 km by 5 km grid of Mahanadi Basin. This is the Mahanadi Basin and this is divided into the grid. Now what I will do, I will overlay this grid over the land use land cover map. Each grid I can calculate what is the fraction of the forest, what is the fraction of agriculture. Then I can use this for my water balance estimation. So then I need AI. So we are taking model AI. Basis, what is the model AI? Similarly, albedo, monthly basis, what is the albedo of different type of crops for agriculture area, for forest area, all these things. This is the input or to the hydrological model. Now this is one report. This is a NETCOM report of IPCC. It says CO2 concentration projection is 542 to 970 ppm. So warming will take place from 1.4 degree to 5.8 degree centigrade in so in 2050 for tropical Asia, annual mean change will be around 2.69 degree centigrade. In winter it will affect more. This is now 3.25 degree centigrade. During summer it will be 2.19 degree centigrade. I force this data in my meteorological parameter and my meteorological forcing file, and then I change the parameter and I got some results. So this is one rainfall of 2008. It is 1378.7. This is average rainfall. However, I have calculated for each pixel. Then 2050 it becomes 1469. So increase in rainfall is 19 millimeter, and you can see this pink line shows the 2050, blue line shows the 2008. So rainfall will increase. So this is my first forecast. Now second, then I estimated the water balance and I found runoff increased by 30%. So it is you can see 515 will increase to 580. It means in 2050 runoff will increase by 13%. So it has a lot of implications. When runoff will increase, there is chances that groundwater recharge will decrease. So if we have estimated, then we found the base flow. What will happen to the base flow? And surprisingly, we found that base flow will decrease. So base flow is decreased. Then evapotranspiration, it is almost same. It is increasing very small, 6%. So again evapotranspiration will increase. Soil moisture will increase little, but groundwater recharge will decrease. So in a nutshell, I can say, if you see this figure, that runoff is increasing, evapotranspiration is increasing, but base flow is decreasing. It means groundwater recharge will decrease, and this is an alarming situation. Down 2050, we will have more runoff, rainfall, runoff, but groundwater recharge will decrease. So now we should plan accordingly. Then we have done this modeling for Ganga Basin also, and we have used IITM Pune model, regional model to take the meteorological data for 20 different years like early century, mid century and end of the century, and we have run the model, and we found this type of hydrograph we have generated for entire year for the Ganga basin, and we found there is an increase in the runoff. So that's how a climate change, suppose there is a change in the precipitation and temperature, it will change the runoff, it will change the runoff pattern. But surface runoff may increase, but base flow will decrease. So this lot of information and a clue for the future planning of the our river basin system. So this is all from my side. Thank you very much.